Hi everyone, I'm Dr. Divya Kaur, and in this lesson we will learn how to write a differential rate equation for 0, first and second order, and we will also derive the integrated rate equations, and also we will learn about half-life of the reaction. So let's begin with 0 order reaction. So let's say in this reaction the reactant A is forming the products. So what is a differential rate equation corresponding to this 0 order reaction? So the rate will be decrease in the concentration of A with time, right? Which is equal to K0 concentration of A raised to the power 0. Why? Because the order with respect to A is 0 for 0 order reaction. Now any variable raised to the power 0 is 1. So concentration of A raised to the power 0 is 1. Now when you substitute that, minus dA by dt will be equal to K0, which is rate constant. This is a differential rate equation. Let's now work on integrated rate equation. So we will move the time terms towards right hand side and the constants, and the concentration terms will be in left hand side. So this becomes minus dA will be equal to K0 dt. Now before the reaction begins, at time t equals 0, let's say the concentration of A is A0. And at time t, the concentration of A is decreased to AT, because during the reaction, the reactant A is forming the product. So concentration of A decreases. So therefore, the integral will be from 0 to t, and this concentration will be from A0 corresponding to time 0 to AT. Now let's move this negative terms towards right hand side. So this becomes concentration of dA with the integral from A0 to AT will be equal to minus, the K0 is a constant, it can be taken out of the integral, and then integral from 0 to t dt. Now as we know, any integral of dx is x. So therefore, integral of dA will become concentration of A going from A0 to AT. And similarly, in right hand side, this becomes minus K0 times t. And then putting the limit from 0 to t. So once you put this limit, final minus initial, this becomes AT minus A0 will be equal to minus K0 t. And hence AT will be equal to, this term if goes into right hand side becomes positive. So this will be equal to A0 minus K0 t. So this is the integrated rate equation corresponding to 0 order reaction. So let's now plot the graph corresponding to this integrated rate equation. Now if you compare with the equation of straight line, y equals mx plus c. Now if the y-axis is concentration of A and the x-axis is this time, so this is an equation of straight line with slope minus k0. So this shows this straight line, and then the intercept will be A0. And the slope is minus k because it's decreasing. So this is integrated rate equation and its graph corresponding to it. Now let's discuss about the half-life of a reaction corresponding to 0 order reaction. So half-life means the concentration of original reactant, which is A0, the original concentration becomes half. At what time? So the AT will be equal to A0 by T at half-life, T half. So what will be the equation, or what is the time corresponding to half-life? So substituting the value, this becomes A0 by 2 instead of AT will be equal to A0 minus K0 T half. Now you move this concentration terms towards left hand side. So this becomes A0 by 2 minus A0 equals minus K0 T half. So when you solve, this becomes minus A0 by 2, which is equal to minus K0 T half. Negative and negative term get cancelled. So T half will be equal to A0 by 2K0. This is half-life corresponding to 0 order reaction. Now let's work for first order reaction. So in first order reaction, again you have concentration A reactant changing to products. So differential rate equation will be minus dA by dt will be equal to K1 concentration of A raised to the power 1. Why? Because order is 1 with respect to A. So this is differential rate equation. Let's now derive integrated rate equation using this differential rate law. So again, time dependent term will be right hand side and concentration terms will be in left hand side. So this concentration is multiplied here, it will be divided here in left hand side. This will be equal to K1 dt. Now let's move this negative towards right hand side and integrate both the side. So again, at time 0, which is initially beginning, the concentration of A is A0, and at time t, the concentration of A is AT. So this becomes, K1 is a constant, it will be taken out of the integral. This negative sign is moved here towards right hand side just to avoid confusion, and this goes from 0 to t dt, and this left hand side will be from A0 to AT dA by A. If you do integral of dx is x and integral of dx upon x is natural log x. So when you integrate this, this becomes natural log concentration A, putting the limits from A0 to AT. And right hand side becomes minus K1 t. So you put the limit, it's final minus initial, so it will be natural log AT minus natural log A0 will be equal to minus K1 t. Now again, this term goes right hand side, so this goes natural log AT will be equal to natural log A0 minus K1 t. So this is integrated rate equation corresponding to first order reaction. Now if you compare with the equation of straight line, if this is your y equals mx plus c, so your x is your time. So when you plot the graph corresponding to natural log A with time, what will you get? The slope is negative K1, so you get decreasing slope with the intercept to be natural log A0. And your slope will be negative of rate constant for first order reaction. Right? Now this is one form of this first order reaction, integrated rate law. We can also have in exponential form. So again, coming back to this, as we know, log A minus log B can be written as log A by B. So log AT minus log A naught can be written as log AT by A0, which is equal to minus K1T. This natural log, when it goes to the right hand side, it becomes exponential. So this becomes AT divided by A0 will be equal to exponential e to the power minus K1T. And therefore, the concentration of AT, this is division here, it will be multiply here if you move. So AT will be equal to concentration of A0 times e to the power minus K1T. So this is exponential form. Again, this is another equation for second order reaction. Sorry, for first order reaction. So when you plot this, this becomes, if you have concentration A here as y-axis and time here, it's an exponential decay. So this is another integrated rate equation corresponding to first order reaction. Now let's talk about what is the half-life corresponding to this. Again, at half-life, concentration of AT will be A0 by 2. So when you put that in this equation, natural log AT by A0, it becomes natural log A0 by 2 times A0 will be equal to minus K1T half. So this cancels. Log 1 by 2 can be written as negative log 2 will be equal to minus K1T half. Negative and negative get cancelled. So T half can be written as natural log 2 by K1. And natural log 2 is 0.693 upon K1. So this ratio is a constant because K1 is a rate constant, and again 0.693 is a constant term. So this is half-life corresponding to first order reaction. So let's now talk about second order reaction. Now in second order reaction, again decrease in concentration of A with time will be equal to K2, rate constant for second order, times A raised to the power 2, because order is 2 with respect to second order reaction. So moving this concentration A term will come here in denominator, and time dependent will go into right hand side. So this becomes minus dA by A square will be equal to K2 times dt. Now again, integrating on both the sides. So at time t0, the concentration will be A0, and at time t, concentration will be A at time t. So now again moving this negative sign to right hand side and K2 outside, this becomes minus K2 integral 0 to t dt, and this will be dA by A square from A0 to AT. Now as we know, the integral of dx is x, and the integral of x to the power n dx is x to the power n plus 1 upon n plus 1. So if you compare this can also be written as integral. If I want to move this in a numerator, I can say a to the power minus 2 dA going from A0 to AT will be equal to minus K2, this is t. So now if we compare by this becomes, the integral will be a to the power minus 2 plus 1 upon minus 2 plus 1, and then the limits will be from A0 to AT. This is equal to minus K2 t. So this becomes minus 2 plus 1. So plus minus minus, if you subtract 1 from 2, it becomes 1, and the bigger one is 2, so negative sign. So this becomes minus of a raised to the power again minus 1 corresponding to this. Going from A0 to AT will be equal to minus K2 t. This negative and this negative will get cancelled. So this can be written as 1 by A, putting the limits AT minus 1 by A0 will be equal to K2 t. Again this term will goes into right hand side. So 1 by AT will be equal to 1 by A0 plus K2 t. So this is integrated rate equation corresponding to second order reaction. Now if you compare with the equation of straight line, y equals mx plus c. Again when you plot the graph with time to be your x-axis and y will be 1 by concentration A. Now if you compare, the slope is positive, so you will get positive straight line with the intercept to be 1 by A0 and slope is K2. So this is the equation corresponding to second order integrated rate law, and this is its graph. Now let's talk about half-life corresponding to second order reaction. So again AT will be equal to A0 by 2 at half-life. So this becomes, when you substitute 1 divided by, instead of AT, A0 by 2 will be equal to 1 by A0 plus K2 t half. Now this can be written as 2 divided by A0, and then 1 by A0, when it comes to left hand side, it becomes minus 1 by A0 will be equal to K2 t half. So this becomes 1 by A0 will be equal to K2 t half, and hence half-life time will be equal to 1 divided by K2 A0. So this is half-life time corresponding to second order reaction. So I hope you like this video. Please like, share and subscribe, and thank you for watching.